Here's problem 1210. A horizontal meter stick supported at the 50 centimeter mark has a mass of 0.5 kilograms hanging from it at the 20 centimeter mark and a 0.3 kilogram mass hanging on it from the 60 centimeter mark. Determine the position on the meter stick at which one would hang a third mass of 0.6 kilograms to keep the meter stick balanced. Let's imagine what's going on here. We have ourselves a meter stick, and it's already positioned on a fulcrum at its center. So at 0.5 meters we have a fulcrum, and we have a 0.5 kilogram mass at the 0.2 meter position. So this is M1 of 0.5 kilograms. And then we have another mass of 0.3 kilograms located at 60 centimeters or 0.6 meters. So this is M2, 0.3 kilograms. And then there's three other forces. We have the weight of the meter stick itself, which is acting on the center of mass or the 0.5 position of the meter stick. We'll have a normal force of the fulcrum on the meter stick, and we don't know what either of those two forces are. But we can use torque equilibrium to eliminate those forces from consideration. So if we choose the fulcrum as our axis, we will eliminate the weight of the meter stick and this normal force because their line of actions go through that point. And so that's what we want to do. We want to select the fulcrum, let's call that rotational axis A, as our axis and solve this problem using torques. We would not be able to solve it using forces because we don't know those forces. So we have to use torque equilibrium, and we need to choose that point to eliminate those forces. Alright, we have a third force of the weight of the 0.6 kilogram mass, and it's located at some arbitrary position. But since this 0.5 kilogram mass on the left has such a good moment arm, it's really got a greater torque than the mass on the right. So we're going to have to put this third mass somewhere on the right here at some position, 0.6 kilograms, and let's just define its position as x. So in terms of from the beginning of the meter stick, this distance here would be equal to x. Okay, so we want to find torque equilibrium about point A. Summation of all the torques about A should be 0. And what do we have? Well, we've got this M1G with a moment arm of 0.3, and it's trying to make this thing rotate counterclockwise, which would be a positive torque according to the right-hand rule. And then we have this M2G over here, and that has a moment arm of 0.1 from the axis of rotation, and that's trying to make this thing rotate clockwise about point A, so that would be a negative torque. And then we have this third torque, which would be M3G, and that's trying to make this thing rotate clockwise as well. That would be a negative torque, and its moment arm is going to be this distance right here, which is going to be equal to x minus 0.5. Will be that distance. Alright, so as we finish this torque equation then, we have a positive torque, which is going to be 0.3 times M1G, and then we have a negative torque, which is going to be 0.1 times M2G, and then we have another negative torque, which is going to be x minus 0.5, I don't have room, times M3G. Alright, so let's write this again. a little bit more clear. So we got 0 is equal to 0.3 m1g minus 0.1 m2g minus x minus 0.5 m3g. If I divide both sides by g, 9.8, I can get rid of the g's. 0 divided by g is 0. And then put in my masses. So I have 0 is equal to 0.3, mass 1 is 0.5, minus 0.1 times mass 2, which is 0.3, minus x times mass 3, which is 0.6, plus 0.5 times 0.6. Alright, so I have 0 is equal to 0.15 minus 0.03 minus 0.6x plus 0.3. In other words, 0.6x is equal to 0.45 minus 0.03, or 0.42, or x is 0.42 divided by 0.6, which will give me 0.7 meters. X is at the position of 0.7 meters on the meter stick, which would be 70 centimeters. And that's the position that we would want to place the third mass in order to keep this meter stick balanced.